Every moment is a fresh beginning. With that, we are here to make your good day a great day. A very pleasant good morning to one and all present here. I welcome you all to the CIT Quantum Hackathon 2022 workshop series, sponsored by IBM Quantum as a part of Quiskit Fall Fest. First of all, congratulations to all the participants for stepping forward to join us because I think participation is more important than winning the competition. All the best, and I wish you all success. Are you guys ready to jump into the world of quantum computing? And yes, finally, the day has arrived to explore new things and gain knowledge. It's my privilege to welcome our honorable chief guest and speaker, Ms. Guncha Malik, Quiskit Advocate. She is a security compliance architect at IBM with 22 plus years of extensive experience in software solutions and information security. She is a Quiskit advocate by passion and pursuing interests in quantum computing via Quiskit community and actively engaged within the responsible computing community and STEM for Girls initiatives. Ma'am, once again I welcome you and extend my sincere gratitude to you for taking your time to share your quantum knowledge and experience. We are so thrilled to listen to your session on factoring integers the Shor's way. The session is now all yours, ma'am.
Thank you, Rasika. Hello, everyone. It is my pleasure to be here. Thank you, Dr. Manjula, for inviting me for this session. Last year as well, I was part of the CIT Hackathon sessions, and it is really nice to visit back. I will share my screen and switch off my video so that there are no challenges in the presentation while I'm displaying my screen. Okay, let me know if you are able to see my screen.
Yes, ma'am. It is visible.
Okay, all right. Thank you so much. So today we'll be talking about factoring integers. Basically, we'll be looking at how the Shor's algorithm can be applied to various industries to solve problems. We won't be focusing with the limited time we have. We will not be able to focus on all the industries, but what we will take a look at is how the algorithm can be applied. Um, all of you must be aware that recently Peter Shor did win the Nobel Prize, and his algorithm that he published in 1994, the Shor's algorithm, as we call it, that really instigated a lot of interest in the industry because until then it was believed that the very large prime numbers that are used for encryption of our data, that is not easily or classically it cannot be factorized and in practical times. So when Shor released his algorithm, it did instigate that interest that an algorithm is possible using quantum computers. However, there was also the challenge that with the known issues and errors that we knew about in the quantum computers, people thought that it would not be possible to implement that in the quantum computer and make it realizable, and hence it did not there was some speculations about how successful that algorithm would be in practical life. But in 1995, Peter Shor came out with another algorithm in which he showed that the noise in the quantum computers can be isolated and fixed. And that is when the race to build computers, the quantum computers, and ensure that the noise is reduced and we can build larger, that is the computers with larger qubits, such that we are able to implement the algorithm. So what we are going to do today is look at the basic problem statement and a few fundamentals we are going to cover, that is the quantum Fourier transform and the phase estimation. Once we are done with that, we'll look at the application of Shor's algorithm to data security and some of the other applications in chemistry and finance. So the first question is, why do we need to find a period? Because that is what Shor's algorithm is really doing. It is finding a period. But why do we really need to find a period? So if we have a function that is periodic, And if we are able to determine its period, then it helps us in solving much more challenges, solving real world problems. And the same periodicity can help us in determining solutions to various things. So if we have a function called fx, which is equal to fy, where x is not equal to y, and the difference between x and y is a constant into period. So this period p is what we are interested in. If we look at any function sine, for example, if we look at wave function sine x or sine theta, we will see that we can easily find the period for this particular function, and it can be determined easily. But there can be a bit more complicated wave functions where determining the period might be challenging. For example, here we don't have a very consistent waves coming in, but still we can see that there is a cycle we can determine. For example, here between x1 and x2 or x3 and x4. But if we look at some more complicated wave functions, it might be really challenging to identify a particular period associated with this. Now, we could be probably looking at a very small section of this, because of which we may not realize that there is more to this, and we can determine if there is a period to that or not. Or we could be too zoomed out, because of which we might not even see the specific periods that are visible. So if we look at expanding this particular wave function, we might realize that there is a periodicity that is coming in this particular wave function as well, which can be determined then using Shor's algorithm. So if we look at how classically this was solved, it really took an exponential time, as you can see from the formula here. And this is the fastest known algorithm in classical computing, where we still need exponential time to determine the periods. If we look at the Shor's algorithm, that will help us in achieving the same thing in polynomial time. And that is where we achieve a little benefit of implementing or executing these functions faster. The reason why we say little is because the coefficient that is included here, that may sometimes be too large, because of which the computation time for Shor's algorithm could also be large. It is really varying, and hence we are saying little, but it is definitely faster than what the classical algorithm can achieve. So Shor's algorithm is basically dependent upon two different algorithms. It is the quantum Fourier transform and the modular exponentiation. And based on this, Shor is able to then focus on the factorization of the very large numbers. So what is quantum Fourier transform? So we will first go through that. Before I start with these fundamentals, I wanted to check, was there any question that anyone would have so far? Or if I'm going too fast, please do let me know. Okay, all right, then I'll proceed with this. So quantum Fourier transform is nothing but changing the basis from computational basis to Fourier basis. And what I mean by that is, when you are, let me switch to the composer here, and I'm going to keep switching the screens from my presentation to the quantum composer to the quantum lab, so that I can show you and practically demonstrate certain things to you. So if you are looking at a single qubit, if we don't have this Hadamard gate applied, basically we have the qubit in state 0. The moment we apply it in Hadamard state, it is in superposition, and you can see the values from 0 at 0 and 1, and there is no phase applied. But if we are applying a NOT gate, rather setting the qubit to 1, you can see that a phase of pi is applied here. And quantum Fourier transform basically does change the from the computational basis to the Fourier basis. That is, it applies the phases. Now, if we go to the Let me go to the lab. Okay. So if I have probably at the end of the session, I'll be sharing this Jupyter notebook as well. But what I'm trying to do here is call out the quantum Fourier transform inbuilt application, function, so that I can demonstrate to you how it changes the states of the qubit. Okay. So here we have a state 000 being considered. I'm looking at a 3-qubit circuit. I'm going to print the computational basis and then plot the Fourier basis for the corresponding state. So when I have 000, as you can, okay, did it come? So as you can see, this is my computational basis and everything is set at 0. And this is my Fourier basis where everything is set at the superposition level plus t, that is, okay. Now, once I change my computation, my initial state to 001, you can see that my that is the qubit 2 here. I'm sorry, I changed it wrong. Since we are working in Qiskit convention, 100. So I have changed my qubit 0 to 1 state. And now if you see, my qubits have really, the phase of all the qubits have changed. This is primarily because my qubits also get inversed in the quantum Fourier transform. But what you can see is my qubit 3, the qubit 2 is changed by a phase of pi. My qubit 1 is changed by a phase of pi by 2. And my qubit 0 is changed by a phase of pi by 4. You can play around with this to see how the phases change as we change the value here, the initial state. And if you look at the Qiskit textbook, you will also find this already implemented for the 4 qubits. So from 0 to 15, they will show you the execution of how the phases change. Okay, so moving back to our slide. So essentially, what are we doing here? We are applying a QFT on the X state, and this is the formula by which we can compute what is the phase applied to the state then. Here, this 2 pi I xy by n is the phase that is applied, and n is nothing but the number of qubits. So 2 raised to the power of n is the value of n here, and n is the number of qubits that we are using. So if we look at a 2-qubit circuit, basically we have our the phase applied to the 0 state and the 1 state. And okay, so when we apply this, we get the plus state. Okay, now this is the phase 0 that is applied. If we are using the QFT on state 1, we are going to get the minus state here. Now, if we apply the same on the n qubits, the formula is just expanded in this manner. And what you can see is there is a phase that is getting applied at each of these 1 states. Because the 0 state would always be a 0 phase, and the 1 state will always get a phase applied to that. Now we'll go to the quantum lab itself, composer itself, and I'll show you the QFT that I've implemented here. Since we wanted to have a bigger font shown here, probably you will not be able to see the circuit easily. What I'll do is zoom out, zoom in between, so that you're able to see the complete circuit after the explanation is done. But basically, I've taken here 4 qubits, and we have 3 in which we are measuring. Okay, so we have the Hadamard gate applied to the first qubit, and then we have U rotations applied based on how I had shown here. Since the denominator here is increasing, 2 raised to 1, 2 raised to 2, 2 raised to n, you will see that the phases applied are slightly different in every case. So from with the Q0, we'll be applying a controlled a controlled rotation on Q0, and we will be applying for the different phases. At the end of it, we'll apply the Hadamard gate, and again, from the different qubits, we are going to start applying the rotations. Once this is done, we need to swap because, as I said, if we perform the QFT, the qubits get inversed, and that is why we need to swap our bits. So here we have done the swapping, and let me see if I can just zoom out. Okay, so here you can see the entire circuit. This is what enables us to implement the QFT. Now here you will see that there is no phase that you are able to see. Everything is coming out as a zero phase. I'm sorry. You'll see that everything is seen as a zero phase. That is because we have not really set any value to any of these qubits. The moment I apply a value to this, you'll start seeing that there are phases being introduced. Another important thing I wanted to share was that the composer allows you to also view the code that is behind the circuit, and so you can see the open chasm format, the conventions of open chasm, in which the code is written here. But you can also look at the Qiskit code, and you have the ability to export this code as well. Now you cannot edit the code in Qiskit. You would have to download it, and probably you can use it in your Jupyter notebook. But the open chasm code here can be changed very easily. So if you want to apply a particular unitary gate here, for example, I wanted to apply a U1 gate, but I don't see a U1 gate here. I applied the U gate, but what I could do is I can go directly here and change the gate to the gate I'm interested in. So instead of CU1, if I want to apply CP, I should be able to do that without any issues. I don't have to necessarily pull out from here. Okay, so once we have the QFT implemented, then we can focus on the quantum phase estimation. And quantum phase estimation is basically allowing us to convert the phase information into the amplitude. So when you apply a unitary matrix to any state vector or eigenvector, it essentially applies a phase to it with the eigenvector remaining the same. So this becomes the eigenvalue, and this becomes your eigenvector. And if we are able to capture this phase, that is what this algorithm will enable us to do. Now, if I go back to our if I go back to our composer. Now, if I want to apply a phase here, let me add. Okay, so I have one particular qubit. Now I can apply Hadamard, and I can get the state of 0 and 1 at the same time. So probability is 50-50. Now, if I apply a phase to this by applying a phase gate, there is this phase I can see over here. But if I look at the probability, that is still the same. And you can always do this by mathematically solving the problem as well to see that whenever you apply a phase, you will still get the probability of 50-50, and you will not be able to capture the application of the phase or what phase has been applied to the qubit. And so what we need to do as part of the quantum phase estimation is that we convert this phase information into amplitude such that we are able to measure it. So the first step in implementing, and first let me show you. Okay, let me show you the quantum phase estimation. I've just done this for 2 qubits here. I've not done it for a large number of qubits so that it's much easier to explain. But you can just expand this to multiple qubits, and you can start playing around with that as well to see how the states really change or the probabilities really change. So here I have taken a 2 qubit circuit. The first qubit is our counting bit, and this is the state, that is the eigenvector that we want to apply it on. So first we apply a Hadamard gate on the qubit 0, that is our counting bit, counting qubit. And then we apply a rotation unitary matrix on qubit 1. After that, I do the inverse because I need to do a QFT dagger in order to retrieve the phase information, and then I measure it. So here you can see there's nothing much you're getting. You're getting that there's a 100% probability that the state is 0. Now, once I apply, that is because I don't have any, this is my qubit 1 is really set to 0 right now. If I set my qubit to 1, now you can see that a phase has been applied. And what I'm seeing is the probability of my state 0 is more than 80%. And my phase probability of being in state 1 is 14.9. So what we have essentially done is this phase that we had, we were able to capture it into the counting bit and implement it into the amplitude itself. The next step that we would have is to retrieve the amplitude, retrieve the phase from the amplitude. So that is how we will implement the quantum phase estimation. And taking that example, the step 1 that we wanted to show here was that there is a 0 qubit and there's a psi state that we have that we've already said. This psi state can be a non-zero, non-1 state, and we can still see how the phases get applied. In step 2, essentially, we are applying the Hadamard gate here. So what you would be doing in quantum phase estimation is for all the counting qubits that you have, you will be applying Hadamard gates, and so you can see the transition happening there. Now, in step 3, we are applying a unitary matrix, a controlled unitary operation, basically on the psi state. And what you will see is after applying the unitary matrix, applying the unitary operator, what we get is a phase introduced here. Okay. Now, after we apply the then we apply the Hadamard gate again, that is the inverse QFT that we are required to perform. And this phase is retained. And what we see is essentially it becomes that for the 0 state, we have certain coefficient, and for the 1 state, we have certain coefficient. So if we start looking at the probability of measuring the 0 state and the 1 state, what we realize is that the 0 state will now have this phase, which was introduced by applying the unitary operator on psi. And that phase has come into this amplitude. And similarly for 1 state as well, we can see that the phase has been applied, and we can now measure it. So this is the overall circuit. If we take n number of qubits, or in this case, the number of qubits as t for counting the state of the phase of the global phase of the state psi. Now, state psi itself could be m qubits. We are not specifying that. And as you can see from the circuit, we are not even measuring it because that is not our interest. Our interest is to capture the phase, which we have been able to successfully do. And then after applying the QFT dagger, we have been able to measure that as 2 raised to t theta psi. And using this formula, we are then able to retrieve the value of theta psi that was applied, that was in the psi state. Now, it is what I showed you was 1 qubit, but considering that since it is very only a small one number, and the probabilities will be much lower, it becomes challenging at times to actually get the real estimation, and that would generally require large number of shots to be done again and again to get the right estimation done. The other way of doing it is to add many more qubits, because that will give you a better estimation, and you can do it in lesser number of runs or shots. The ideal number of qubits that are required as counting qubits is 2n. That is the number of qubits that we have in psi. At least double the number of qubits are required in the counting for counting the state. Counting the phase. Okay, any questions so far?
Yes, ma'am. I have I have a question.
Mm-hmm.
Ma'am, in the last slide, can you go where you showed that unitary Yeah, yeah, this one. So here, the e power I theta psi. Here, what psi is in the power of e is the eigenvalue, and in the this k vector. So this is eigenvector, and in the power of e, this is eigenvalue, right?
So this, I'm assuming you're talking about here, this section where I'm pointing.
Yeah, 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 yeah.
Yeah. So psi is the eigenvector. This psi is really not. It is assigned. It is the subscript of theta, just to indicate that this theta is related to psi. It is not the state itself. Okay. So it's only I theta. It's e raised to I theta, which is the eigenvalue, and psi is the eigenvector.
But ma'am, my research area is also quantum state transfer on graphs, and I'm
Mhm.
studying this transition matrix in my research.
Mhm.
So this is actually solution of Schrodinger equation,
So
in
this is,
which
yeah, this is not Schrodinger equation. What we
solution of
what we are
Schrodinger
trying to
equation.
show, yeah, what we are trying to show here is the unitary operator when it acts on psi.
Yeah, this
That
is
is,
representing the state of the qubit. The
yeah,
psi is representing the, and in the power of e, it is the eigenvalue. And with the u, means in the kate vector, it is the respective eigenvector. That's what
mm,
we study in
right,
our.
right. So all we are saying is that QPE algorithm is going to enable us to retrieve the value of this theta. So this is not QPE algorithm. What we are trying to say is once we have the unitary operator applied, there is a theta that we are not able to measure, and QPE allows us to measure this theta. Does that make sense?
Okay, okay, ma'am. Thank you.
All right. Any other questions? And I know that I'm not showing all the calculations in detail here because it will be really challenging to cover all the content in the short time and as well as go into the depth of each and every calculation. But these calculations are really interesting to do, and I would definitely recommend that all of you try it once at your end. That gives you a very clear perspective of how why the circuits are behaving in the manner they are behaving. Otherwise, they just seem like boxes. All right. So now we go to the Shor's algorithm and why, where it is applied and how it is applied. So why did Shor's algorithm really create so much interest in the industry was because the data encryption that we have, the digital data encryption that we have. At some places we have algorithms that are really relying on factors of very large integers, and these factors are also prime factors, which are very large numbers, and it is classically difficult to factorize these numbers to identify the prime numbers associated with the integer being used in such encryption. But Shor's algorithm did show that it was possible to do it much faster than what classical algorithms do, and with the possibility that errors in quantum computers could also be reduced. This did bring the threat closer than what others had anticipated, making the entire industry to start looking at how, first of all, the errors can be reduced and quantum computers can be implemented. But secondly, to also see how we can now, how do we now protect the data that is relying on such encryption? If you look at some of the statistics, and this will be available on the internet also as based on various research that is going on and has been done in the past as well. For RSA 2048, if you there was a paper published in 2019 which said that it really required so many qubits, physical qubits, in order to break the encryption. But in 2021, in just 2 years, there was another paper published that showed that it was possible to do it with just 13,000 qubits, 13,000 plus qubits. Now, if you look at the roadmap, and I'm going to just talk about the roadmap that IBM has published, and we did update our development roadmap this year itself to show how many qubits we would be launching in the future. Last year, we did release our Eagle chip, that is 127 qubits. This year, we are on target to release 433 qubits. And as you can see, it is still nowhere close to what the research papers have shown so far. But if you look at our future roadmap, we are planning to have many more qubits released. And so that it doesn't now seem improbable to have such large number of qubits in practical quantum computers anymore. There's a lot of work being done in terms of reducing the errors, that noise itself. So that should also enable a faster development. And it is not just IBM, but many companies who are in this race of developing the quantum computers and implementing noise correction, so that we can have much more higher number of qubits, and at the same time they are stable enough to implement the practical computation that is required. So with this, we go to the Shor's algorithm of finding factors. We already discussed the problem earlier. We know that we have encryptions that are really based on these numbers, which are using very large prime numbers. And if we are able to generate the factors of these very large numbers, then it is easy to break the encryption, which makes it challenging for us to protect the data, which is these days really the gold, you can say, of today. So with that, this is the function that Shor's algorithm is relying on, where function of x is equal to a raised to x mod n, where a and n are co-prime, and these are positive integers. A is any constant which is less than the value of n, and I did not mention here, but n is basically a very large integer, which is a multiple of two very large prime numbers. The x here is really the period that we are interested in, and what we are saying is that a raised to the power n r, where r is the period. In this figure, r is equal to 12. You can see a raised to the power r mod n is equal to 1. We are interested in the smallest r that's possible to find the periodicity of this particular wave function. So these are the steps that are there in Shor's algorithm. Now, it should be noted that Shor's algorithm is comprised of the quantum side of computation, and there is a post-quantum computation as well, which is required to be done on classical computers. So it's a combination of this which helps us in finding the factors. In terms of the quantum computing side of the algorithm, the first step is really to find a. This is an assumption that we make such that it is co-prime with n. Now, when we say it is co-prime with n, that is none of the factors of a and n are common. Once we define a, we need to, we can always check whether there is a common factor or not. The GCD of a and n should always be 1. That ensures that these are co-prime numbers. So we validate our first step is accurate. The second step is to find the order n, and that is done using this formula. Now, the smallest r that we find, we need to check if it is even or not. If it is even, then we go to the next step of identifying what is the value of x here. And if the x plus 1 is not 0 mod n, then we can say that one of the two prime numbers can be determined by GCD of x plus 1 n or GCD of x minus 1 n. But if the value of r is odd, then we have to go back to step 1 and pick another a. So this is how we need to perform the computation here. Once we are confident that one of the numbers P or Q has been determined using this method. Then we go to the classical side, and then we use the formula J equal to N by R, where J is some integer, N is P into Q, and R is the period that we have identified from here. And what we are going to try and do with this is determine for the various R's that we have found, which is the possible value where we will get the required J function, J and N, such that the period is close to what we are looking for. Now, when we start applying all the values, and this is a very complicated calculation again, the different values that we can retrieve from that calculation, which have to be applied here. The reason why I'm not going into that is because we won't have enough time to cover that and explain the remaining stuff here. But I do suggest that you do go through all that calculation, because that will give you a better insight of what are the different values that we have to try and assume the values of J, so that we can retrieve the values of R based on that. There is a series of sessions that Abe Afshaw had taken in 2020 as part of the Kiskit Summer School. I would recommend that you do go through those sessions as well, because he has taken quite tremendous efforts in terms of explaining the entire calculation there. It is really insightful to do it yourself once, so that you understand how the calculations are really resulting into the integers that we are able to identify using Shor's algorithm. But what essentially we will see is that the results after all the combinations that we run on classical computer, they will peak near the period that is the right period, and that is the period that we can select as the one that we want to use. Okay. So Shor's algorithm is basically implemented, and I'm just going to show you the circuit here. It basically, here we have the 4 counting qubits. This is the circuit, and what we're going to do is apply a unitary function here, where the function is a raised to the power x mod n. After the unitary function is applied, we apply the QFT dagger to retrieve the phase, and then that helps us to determine the prime numbers. If we are able to identify even a single prime number, then we will be able to calculate the period, and yeah, that is what we will be doing. So what I want to show you is that this unitary function that we're talking about is nothing but quantum phase estimation in disguise. We keep talking about Shor's algorithm, but if we look at the circuit, it is essentially the quantum phase estimation that has been implemented. So this is the Shor's algorithm implemented. We have all the Hadamard gates, and then we have the unitary rotations applied, and then we have the QFT dagger, which results into the value. Okay, so this is how Shor's algorithm is implemented. We can find factors, and I wanted to take a quick check if there were any questions on this. If not, then we'll just go to the lab and take a look at one such algorithm. Okay, so let me go to the lab. So classically, we were talking about N and A being some constant that we have identified. So let me just find, take N as 5 by 3, that is 15. I'm going to take only small values because that is what will be easy for us to run right now. And even our quantum computers would not be able to take large numbers. But if I take the constant A as 7, this is the first number that I picked up. I check whether the GCD between A and N is 1 or not. And all this calculation that I'm showing you here is only classical implementation right now. I'm not going to the Shor's part at all. Now here we have looked at how the wave function looks like. So as you can see, there is periodicity that we can identify. Now we can find the period using this formula, and we will see that it keeps repeating. The y value keeps repeating, and so we know that the r is equal to 4. the difference between two ones is equal to 4. So this gives us the factors we have calculated on the basis of x plus 1. And so we have done all those steps that we were talking about here. Let me go back. We have done all these steps. We have looked at the n equal to p into q. We have looked at the GCD. We have identified the order. And then we are at step 3, where we are looking at whether the x is equal to a raised to the power r by 2 mod n. And this x plus 1 is not equal to 0 mod n. So that is what we are checking here. And once that is done, then we can identify the factors. And we have identified the factors as 5 and 3. Implementing this in Shor's algorithm, as I said, I'll be sharing this Cascade, this Jupyter textbook as well, notebook as well, so that you can run this yourself. But basically, we have done all the imports here. Now, for every mod, there's a different function that is required to be written. What we have done here is we have used mod of 15. This is a different number that we are using. So we have, I think 7 is what I'm using here. Okay, we'll see down what numbers we are using. So mod 15 is what we are using here. This function is looking at where a is not equal to these numbers. If it is, then we just have to throw an error. Then we are building the quantum circuit where we are then swapping the gates, swapping the qubits to make sure that we are able to get it in the right convention. Then we have the QFT dagger implemented as well. This is to apply at the end. And then here we are using n equal to 15 and n count as 8. So let me just quickly run these functions so that when we call them, they can be applied easily. Okay, so I have run those functions and now I have these values set as well. Now for picking up the value of A, we are using a random seed, and the reason why we are putting in a seed here is so that we can get a consistent result. Otherwise, if we remove this, the value of A will be random, and we might not get the right value every time. So we might have to keep attempting it again and again. So here we have now checked A is 13 and N is 15. A is smaller than N, which is right. And then we have GCD is 1 between the two, which is good. So we can now go ahead and execute our circuit. Okay. So once we apply, now this is where we are running the Shor's algorithm, where we are now calculating the phase by applying the QP A mod 15 function that we had applied earlier. Then we are looking at the phase. We are calculating the phase, and we are then running the inverse QFT. Now, what it does is it will do multiple attempts to see whether it is getting the right set of values or not. And you can see all the calculations being done here, the circuit being generated. R is equal to 4. So at the first attempt itself, you can see the circuit was able to identify the guessed factors as 3 and 4, which are non-trivial because they are not 1 and they are not n, so it seems relevant. And so we have been able to factorize it. Now, Qiskit gives you an inbuilt class called Shor, which you can easily use rather than doing all the calculations for different mods and different values of A. All you need to do is have your, and let me run this for you quickly. You can create your backend simulator and quantum instance, and you can then call the class Shor with your quantum instance as the input. Now, in the Shor result, you can give the factors of n, give the values of n and a, which we had already provided earlier. So n was 15 and a was 13. When you run, you'll get the result and in the Shor result itself, and you can always print it. It will take some time to do the calculations, but you can print it and you will be able to see the results here. I'll give it a minute to run. So as you can see, it does take a little longer sometimes. So here you have identified the factors as 3 and 5. In 2 counts itself, we were able to, 2 successful counts, we were able to determine that the factors are 3 and 5. You can also run it on IBM Cube provider provided uh, s- um, real machines, and you can just do it by calling the IBM Cube provider here. You can also find which backends are available and least busy. So I've provided that code as well to you so that it's handy for you. So with that, we are done with the Shor's algorithm for data security, that is factorizing the integers. Any questions so far? Okay, then moving on to the next one. So how can we apply Shor's algorithm to chemistry or to nature, right? Uh, when we think about nature, nature would comprise of chemistry, biology, and physics as well. So basically, wherever, and it's not that Shor's algorithm can is entirely implemented at every place. It's since Shor's algorithm is comprised of different components, those different components themselves can be applied to solve certain challenges in different industries. So if we look at the chemistry, we do have a periodic table where chemists have put all the elements in a single table and they have categorized them by groups. But determining the chemical periodicity enables the chemists to understand how these elements are related to each other, what are the common properties they have, should they be grouped similar should they be put into one group because of the properties they possess. All that can be determined if they look at the periodic function of these chemical elements. Uh, there is there is molecular periodicity or atomic periodicity that can be used, and they can really identify formation of new compounds itself if they are able to determine how the compound would behave. There are other new elements that are yet to be discovered for sure, and they will be able to determine much more once we are able to apply these concept of periodicity using Shor's algorithm or components of Shor's algorithm. In the world of finance, market data analysis is quite complicated. This is required to be done on a daily basis, weekly basis, hourly basis, and it really helps the analysts to determine whether the market, how the market trends are, and when the market would start going up or down, and when the investors should start investing, right? So, considering that, there are three different periodicities that are of interest when we look at the market data: the time dependent periodicities, the volume dependent periodicities, and the price dependent ones. And all these are, there are numerous charts they generate on a daily basis, hourly basis to show how the trends are moving. If we are able to apply, and I personally have not worked on it, but if we are able to apply the periodicity to complex problems that cannot be easily determined by our classical computers, that will give much more insights for the analysts to take the actions and predict the next steps. These are some of the references that I would like to share. I have links to the quantum labs, but importantly, I also have the links to Abe Afsar's sessions, which I really feel are quite helpful if anyone wants to start. Go to the basics of understanding how the phase estimation is done, how the calculations are done, how does it get applied, how does it get transferred. All that can be easily understood by going through these sessions. These are about 5 to 6 hours of sessions, basically 6 sessions in altogether. And then I would be sharing my lab as well, files, so that if you want to go through it, you can go through it later. These are this is a good conceptual paper on periodicity for chemistry. This is where I read about how the chemical periodicity is important and what role it plays. And then I have also given you the link to the chart periodicity for finance markets. So with that, I am at the end of our session. Is there any question for me? I'll switch on my video. All right, Dharni, I think there are no questions. If there is anything, please let me know. I'm sorry, Dharni, I didn't understand.
No, it was here. Sorry. I think there is no questions. So.
Okay.
Thank you for your comprehensive session, ma'am. And I hope we have arrived at the end of our session. I once again thank Ms. Guncha Malik for joining hands with us to make this session a success. I would like to thank Dr. Manjula Gandhi for leading us and supporting us throughout the process. And I thank each and every one of you for joining the session. Stay tuned in the Discord server for announcements and updates. Recorded video of this session will be posted on the same. And as always, feel free to post your doubts and queries in our Discord server. We are always there to help you guys out. And timings and links for further sessions have been circulated through Discord channel. And meet you all in the next session by Mr. Vishnu Ajit at 11:30 a.m. I thank you all on behalf of Team CIT Quantum Hackathon 2022.
Thank you, Risika. Thank you, everyone.
Thank you, ma'am.